in today's lecture, we're going to be talking about calorimetry problems, which is a fancy term for any type of problem you encounter in chemistry where we're trying to think about how heat changes during a normal process or during a chemical reaction. And so calorimetry problems get used all over the place, from chemistry to food science to even what happens if you make yourself a boiling cup of hot chocolate and you want to add a little bit of cold water to cool it off, but not cool it off too much. And so I think what makes calorimetry problems really exciting and interesting, they're some of my favorite class of problems, is that the range of applications is so broad. But I think on the student end, when you're learning these problems for the first time, students think calorimetry problems are really hard. And I think there's a couple of reasons for that. And so our goal today is going to be to work through a couple of concrete examples where you might see some of these calorimetry problems and to focus on the aspects that are typically challenging for students so that we can work through more systematically how you should approach the problem solving aspects. Okay, so what makes calorimetry problems hard? I think the first thing is that there's a lot of equations. Calorimetry problems are always going to ask you to solve for heat, that variable Q, but Q equals MC delta T. Q equals capital C delta T. And now we've just introduced that also at constant pressure, Q is equal to delta H, the enthalpy. And so knowing when we're talking about heat, which of these three equations to apply and where can be really challenging. A second thing that I think makes calorimetry problems challenging to solve is that the units can be really tricky. In our equations above, oftentimes they won't give you the letters to represent the variables, they'll simply give you numbers in a word problem and associated units. And so something that we're not going to talk about a lot in today's video, but you want to make sure and pay attention to is that the units are going to tell you which variable a problem is giving you. Specific heat capacities, that's lowercase c in our equation list, is always in units of joules with grams and degrees Celsius in the bottom, so joules per gram degree Celsius. Heat capacities, capital C's, are given in joules per degree Celsius. And then enthalpy is even trickier. Sometimes you'll see enthalpy reported simply in units of joules. Sometimes you will see folks ask instead for what's called the molar enthalpy, which is going to be units of joules per mole. I typically, when I am working with students, try and change up my variables a little bit. So I might often refer to normal enthalpy as delta H, and molar enthalpy as what we call delta H bar, so something that has a little bar over it. You're not going to see this frequently in textbooks, and sometimes people will say enthalpy when they mean molar enthalpy. So really pay attention to the units so that you know what we're talking about. And then last but not least, the third thing that makes calorimetry problems really challenging for students is that typically if you go into your textbooks or you watch YouTube videos, you're going to see a lot of equations show up that weren't in these blue equations that I showed earlier. And so you might, a lot of students I see in their notes will start writing down Q metal equals negative Q water, Q calorimetry plus math, like it gets really complicated. And so knowing where did these equations come from and how is that just supposed to be represented as intermediate scratch work specific to a particular context and a particular problem so that we don't get bogged down in these unnecessary equations, I think that's the third thing we want to go through. And so what I want to talk through next is I think there are two underlying principles that are really going to help us understand how to not focus on these equations that I don't want you all to memorize, but instead focus on how can we treat these underlying principles as a toolkit that's going to help us set up a particular problem for a particular context in a way that makes sense. The good news is both of these principles are pretty common sense, pretty straightforward. The first principle I want to talk through is what's called heat conservation. In words, what we would say is that when it comes to heat, we can transfer heat from the system to the surroundings. We can transfer heat from the surroundings to the system, but heat is never going to be created or destroyed in a particular process. And so in equation format, what we might say is that Q, all of the things that are gaining heat, and plus all of the things that are losing heat is going to be equal to 0. This might not feel intuitive in a heat context, but I bet you if we think about it instead in terms of our bank accounts, that it will make sense. So if I have just get a paycheck, which goes into my checking account, I might transfer some of that money that I just gained to my savings account. And I might transfer some more of it to a different place. Maybe I store it in my credit card or in Venmo or something along those lines. And so if I take $50 from my checking account and I put $30 of it into my savings account and $20 of it into my Venmo, well, guess what? I've just showed that I have moved around money, but I haven't gained additional money and I haven't destroyed additional money. I've just simply moved it around in where its location is. And so if I put some numbers on this, hopefully you can see that -50 plus 30 plus 20 adds up to 0. And so this equation that I have in blue, even though it might look different in different contexts, depending on how many objects are in the system, how many objects are in the surroundings. So we might add additional terms. You can see in blue, I've got 2 terms, kind of just the lump sum of things that are gained versus the lump sum of things that are destroyed. But if you think about it conceptually this way, of all of the sources of heat, whether those things are gaining heat or losing heat, has to add up to 0. That's going to be what helps us set up all of these practice problems. I'll point out what I'm showing in pink is that sometimes folks like to mathematically rearrange this so that instead of adding up all the terms equal to 0, they'll say that all the things that gain heat are equal but opposite sign compared to the things that lose heat. That's totally fine if you want to do it that way. It's mathematically equivalent. You'll see me using the blue version of the equation because that's the one that makes a little bit more sense to me. Okay, principle number 2, this one probably feels even more intuitive. Hopefully it matches your real world experience. And the fancy term for this is temperature equilibration. It's the idea that if I have 2 objects and I place them in contact with one another and I let it sit for a little while, once these have had a chance to sit and equilibrate, they're going to reach the same temperature. And so you've probably seen this before. If you've ever mixed together hot water and cold water, you know you're going to end up with warm water. But it's not like the hot water, it's not like half of the cup ends up being hot water and half of the cup ends up being cold water. Instead, things mix together and they arrive at the same temperature. And so we can use this principle of temperature equilibration. If you feel like you're not given enough temperatures in the problem, you can think through what of these things are in contact with each other, and have the system been given enough time, then you can say, oh, these temperatures must be equal to each other. It's going to be the same temperature. Okay, so those are our 2 principles. Let's go ahead and think through now how we're going to solve these calorimetry problems. And instead of giving you the steps all at once for solving a calorimetry problem, what I've decided to do is put this in the context of a practical example. So the math example we're going to work through right now is going to ask us to predict the final temperature of a mixture when we add 100 grams of water at 90 degrees Celsius to 400 grams of water at 10 degrees Celsius. If you want to think about this in terms of pictures, you can look at the picture above. Our temperatures aren't quite the same, but it's going to be the same idea. We're taking a cup of hot water, a cup of cold water, and we're mixing them together. It gives us a little bit of data in the problem, and we'll use all of those numbers in just a minute. But first, the thing we want to do first in calorimetry problems is not start plugging things in right away, but instead to think through how these 2 underlying principles that I just mentioned apply, and can we translate them into a mathematical equation that describes our system for this particular context. So for the first principle, I would say it seems to me like we've got 2 objects in our universe that we care about. We care about the cup of hot water and we care about the cup of cold water. And the subscripts that I put down here are arbitrary. They're helping me bookkeep. So if you like to write down Q sub H plus Q sub C for the hot and cold water, if you want to write down Q hot water, Q cold water, do whatever you need to do to bookkeep it. But I would recommend using subscripts so that we can keep these distinct Qs, well, distinct. So in this case, I've identified the 2 objects that are in my universe that I care about and that I think might be doing some heat transfer. And I'm going to set them equal to 0 because I know the principle of heat conservation. The sum of all the ways they're transferring heat has to add up to 0 because heat is not leaving this universe and is not entering this universe. The second thing that we want to think through as a principle is how might the temperatures of these systems be related? Obviously, initially, when these are 2 separate cups that are not in contact with each other, they're going to have 2 different temperatures. And we see that one of them has a temperature of 90 degrees Celsius and one of them has a temperature of 10 degrees Celsius. But after I mix them together, we've got 2 objects that are in contact. And so that means that the temperature of the final mixture when we think about the final temperature, well, it's the same final temperature for both pieces of the system. They're in contact, so they're going to be temperature equilibrated. This now is enough. We've thought through the two underlying principles, and so it's enough for us to move on to the second step, where we're now going to think about these cues in terms and relate them using all of the equations that we discussed last class for how these cues relate to the things that are actually given to us in the problem, like the masses, the initial temperatures, the final temperatures, and the heat capacities. And so I've categorized the three big equations that we were talking about last time into two categories. One category is these sort of like heat capacity or specific heat capacity equations. I think anytime you visualize your system as gaining or losing heat through a physical process, like water heating up or water cooling down, you want to use one of these two equations, Q equals mc delta T or Q equals capital C delta T. It's pretty common to be confused about which one of these is most appropriate. And so I always tell students for this, if you're having trouble distinguishing between them, just focus on the units. Our Q equals mc delta T. If you get a number and it's given to you in units of joules per gram degree Celsius, you want to use this leftmost equation. But if you're given a heat capacity, something that has units of joules per degree Celsius, you want to use the equation that's on the right. So looking at our problem statement one more time, it looks to me like we've got a specific heat capacity of water. It's in units of joules per gram degree Celsius, and so that means for our problem in just a moment, we're going to use this Q equals mc delta T equation. Not necessarily for this problem. I don't think we have any chemical reactions going on. We're not breaking and forming bonds in this water. But for other problems we'll see in this video, sometimes you end up with chemical reactions. And for those, we typically as chemists think about heat in terms of enthalpy. So if we can assume, and you can for most systems unless it tells you otherwise, if we're at constant pressure, for every Q that you see, you can simply sub in delta H, the enthalpy. And so for chemical reactions, that's the substitution we're going to want to make instead. Okay, so how does this apply to our problem? We have two Q's that showed up in that equation that we came up with, and for each of those Q's, we want to substitute in an appropriate expression. For the hot water, I think it's undergoing a physical change. It's probably going to cool off, and the information I have about the water in terms of its heat capacity is its specific heat capacity. So I'm going to substitute in mc delta T, and for organizational reasons that hopefully will be clear in just a moment, I'm going to use subscripts to help me keep track of my bookkeeping. Because in my problem statement, I've got two masses, and I want to make sure I don't plug in the wrong one. So I'm going to say m sub hot to make sure I plug in the number for the hot water, times the specific heat for the water, times, and here, because delta T is not going to be the same for both parts of my system, again, they're ending at the same temperature, but they're not starting at the same temperature. So I'm going to say delta T is T final minus T initial, and you'll notice with my subscripts, I just said T final, but for the initial temperature, I was very clear to specify this is the initial temperature of the hot water, because it's starting off at a different temperature from the cold water. Okay, so for the first Q term, we've got mc delta T. Now we're going to do the same thing for the second term. I don't think there's anything conceptually different that's happening to the cold water. Yes, it has a different initial temperature, it has a different mass, but it's still that same process of it's undergoing a physical change of heating, not a chemical change. And so I think mc delta T is also the appropriate thing to substitute in for this term. And once again, I'm going to use subscripts to help me later on with my bookkeeping. Okay, so now this is starting to look like a problem we can actually solve. Once you have an equation where you've substituted in something for both of your Q's, now you can go ahead and move to the third and hopefully final stage of most problems, which is the algebra stage. So at this point, we can go ahead and just plug in all of our numbers and solve for our unknown variable. In this particular problem, we are told all of the information that you need except for T final. That's the thing that we're trying to solve for. It shows up twice in our equation, so we have to be careful, but that's going to be the unknown variable. Sometimes, and here's a good example in this problem, if we're a little bit smart, we can probably avoid having to plug quite so many numbers into our calculator. Something I'm seeing here is that if I'm clever and I divide both sides of the equation by the specific heat of water, Well, a whole bunch of terms are going to cancel. And 0 divided by any number is simply 0. So the first thing that I've chosen to do for this problem is an optional step, is I've noticed that I can cancel it out of my equation. That way, when I go to actually plug in my numbers, I've got fewer numbers to plug in. You can see in this line that's on the bottom of the screen, me plugging in all the numbers from the problem. It told us the hot water had a weight of 100 grams and started at a temperature of 90 degrees Celsius. And remember, the cold water started at 10 degrees Celsius and had a mass of 400 grams. The next thing that I'm going to choose to do in terms of my algebra is we've got a couple of distributions that we need to do. So remember, when we have to do the multiplication, we've got to distribute all of our terms. And so this is going to give me 100 grams times T final minus 9,000, who knows what, degrees Celsius times grams is, but that's just bookkeeping our units. And then we've got 400 grams times the final temperature minus 4,000 degrees Celsius times grams. The last thing that we're going to do is we're going to combine like terms, and just like we're solving for x, solve for our unknown. So combining like terms gives us 500 grams times the final temperature minus 13,000 grams degrees Celsius. That's equal to 0. Rearrange a little bit by adding 13,000 to both sides. And last but not least, divide both sides by 500, and that's going to give us our final temperature and our final answer to this problem, which is 26 degrees Celsius. Okay, I always recommend for any practice problem, but especially calorimetry problems, double check that your answer makes sense. Here, what I know about this problem using my common sense and my real world experience is that I started off with much more cold water than my hot water. So I know when I mix together a hot thing and a cold thing, we're going to get something that has an intermediate temperature. But because I had much more of the cold substance, I feel like my answer should be closer to 10 degrees Celsius than it should be to the 90 degrees Celsius. And so 26 degrees Celsius seems pretty sensible to me. And that makes me feel a little bit more confident, especially if I'm in a test situation where I can't look up the right answer, that I'm probably on the right track here. Okay, let's do one more example before we finish off this video. This one's definitely a little bit more challenging, so we're going to go through it together, but something that I want you to see as we do this very unrelated problem is that the steps and the way we should think about the problem solving is going to be the same. Okay, here's our next problem statement. It tells us that 0.1 moles of barium nitrate is added to a calorimeter at 25 degrees Celsius, and the calorimeter currently contains 0.08 moles of sodium sulfate and 200 milliliters of water. After we add the barium nitrate, it says the temperature increases to 50.54 degrees Celsius. And our goal is to determine the reaction enthalpy per mole of barium sulfate. So right away, I know that something that we are looking for in this problem is if it wants us to give an enthalpy, that means that we are solving for delta H, and we better end up with units of joules per mole, or if we feel like it, kilojoules per mole. This problem didn't specify, so I'm probably at the end of the problem going to pick whatever feels like the number that I don't have to put in scientific notation. All right, and then last but not least, it looks like it gives us a little bit of information. We've got the heat capacity of the calorimeter, we've got the specific heat capacity of the water, and then we've also got the density of the water. I don't know how I'm going to use these things yet, but that's a problem for later, because step one is still to think through the underlying principles and how they relate to our problem. So in terms of heat conservation, unlike the last problem, now I feel like I have way more than two things in my system that might be gaining heat and losing heat. One thing that we have is, especially if I draw a little picture of our situation, we have a calorimeter. Fancy calorimeters, if you were in like a food science or the food industry, would be pretty complicated and expensive to make sure all of the heat really does stay put and doesn't leak out into the air. A lot of you will go on to do in your chemistry lab what we call a coffee cup calorimeter, which is just a couple of styrofoam cups stitched together. But a calorimeter is just the container that the water is going to be in. And then we also know we've got the water And then we've got our chemicals inside of the water. And we'll talk about this in a moment, but it turns out that this barium nitrate is going to react with the sodium sulfate. And so really in broad strokes, what we've got is a chemical reaction going on. So it's possible to think about this system as having multiple pieces. We've got the reactants, but we've also got the products, and there's lots of different chemicals going on. So a tip is when you have lots of chemicals in a system, but you know they're all reacting together, I would recommend combining all of that information into one single term for Q, which we'll call Q of the reaction. And that's going to help us with the math too, because we're not asked for the specific heat of the different reactants or the different products. We're just asked for the overall reaction enthalpy. And so one of our terms should be Q reaction. And that takes care of this piece right here where we have all of these chemicals interacting with each other. The second thing that could be gaining and losing heat is the calorimeter. I know when you have your coffee mug, especially if it's a fancy brand like Yeti or Stanley, you like to hope that your coffee mug isn't gaining or losing heat, because otherwise your coffee is going to get cold over time as the heat goes into the coffee cup itself. But realistically speaking, some heat does leak into the calorimeter, and so especially since we're given the heat capacity of the calorimeter, we should take that into account and add that as its own Q term. And then last but not least, we've got the water. Clearly the water is changing temperature, and so that's a good sign that the water is gaining heat, and we should definitely include it in our expression. So ultimately for this, I've got three terms that we're going to worry about. We're going to worry about how the reaction might be changing heat, the calorimeter might be changing heat, and the water might be changing heat. And just like we did in the previous problem, due to heat conservation, when I add up all of these sources of heat change, that should add up to 0. Our second principle, which helps us think through the temperature equilibration, tells us that when our calorimeter, before we added the other chemical, it was at 25 degrees Celsius. But we didn't need to specify that both it and the water were at 25 degrees Celsius because they were in contact with each other. And so that means that they have the same temperature. And since the whole system is in contact, that means that everything also has the same final temperature. And so for this problem, unlike the last one, since everything starts at the same initial temperature and ends at the same final temperature, I can combine that information together right away and say that anytime I see a delta T for this particular problem, it's just T final minus T initial, which if you plug in the math, happens to be 25.4 degrees Celsius. Okay, so now that we've thought through the principles, now we can think about what we should substitute in for each of our three Q terms that we have. I would say for the first one, this is obviously a chemical reaction. And so where I see that Q reaction, I'm going to substitute in delta H. For the next term, I've got my calorimeter. It's not undergoing a chemical change, it's just heating up along with the rest of the water. And so the reason why I'm plugging in capital C delta T rather than MC delta T is simply because of the units that I was given. Notice in the problem statement, when it gave us the heat capacity of the calorimeter, it was in units of joules per degree Celsius, not joules per gram degree Celsius. And so that tells me that I should be using capital C delta T, which is in contrast to our third and final term, the water. For the water, we're given the specific heat capacity. And so on that, I'm going to plug in MC delta T for my formula. Okay, so that's all set equal to 0. And now it's time to do the algebra. This one, actually, the algebra, I think is a little bit easier than our last problem. The first thing I'm going to do is I'm going to rearrange the equation. So if I subtract off my second and my third term, that'll allow me to get delta H by itself, which is the term that I'm trying to solve for. And now I can pretty much plug in numbers. I'm told the heat capacity of the calorimeter. We calculated delta T a little bit earlier. We know the specific heat capacity of the water. The only one that's a little bit tricky is we were told not the grams of water, which is what we're looking to plug in, but actually the milliliters of water, the volume. And so we need to use, why did they give us the density? We need to use the density real quick so that we can convert from milliliters to grams. And because the density is 1 for water, this tells us that 200 milliliters of water is equal to 200 grams of water as well. All of those numbers, then we can simply plug into our calculator and we get an answer for the enthalpy as negative 2.66 times 10 to the 4 joules. You don't have to do this, but I like to convert this number to kilojoules so that I don't have to deal with scientific notation. So this is going to be negative 26.6 kilojoules of heat. So it feels like we're done with the problem. The only hiccup is that it asked us to report our answer in joules per mole. And right now I've got joules. So oftentimes in these calorimetry problems, there's going to be kind of a part B to the problem where once you've solved for the heat, you might have to deal with the underlying stoichiometry problem. If this reaction and the way that I balanced it doesn't seem familiar to you, go ahead. I've linked in the description a couple of videos about how we handle precipitation reactions, and there's also some good videos on how to do stoichiometry problems, thinking through limiting reagent, as well as these mole-to-mole conversions. But our balanced chemical equation is, well, this is actually a precipitation reaction. So when we react barium nitrate with sodium sulfate, we're going to do a double displacement reaction, and the products we're going to get are going to be barium sulfate and sodium nitrate. So if you were wondering at the beginning of the problem, where is this barium sulfate that they want the answer in terms of coming from? Well, it's coming from, this is one of our products. And so this, now we want to figure out the moles so that I can take my heat and divide it by the number of moles. And just like any other stoichiometry problem, we want to, when we're given multiple sources of moles, here the barium nitrate, we know the moles of that, the sodium sulfate, we know the moles of that. We want to make sure we're thinking about the limiting reagent so that we can predict the quantity we're actually interested in, which is how many moles of barium sulfate is there going to be. Because this stoichiometry is all one-to-one for the quantities that we're interested in, it's pretty easy for me to spot without having to do the math that since everything's in a one-to-one ratio and I have the least amount of sodium sulfate, clearly that's going to be our limiting reagent. And so the moles of sodium sulfate, if I have 0.08 moles of that, and my balanced equation tells me that that is in a 1-to-1 mole ratio with my barium sulfate, then we can know that the moles of barium sulfate, which is what we're asked to calculate and report our answer in terms of, well, that's simply equal to the moles of sodium sulfate. So my moles of barium sulfate is going to be 0.08 moles, and that allows me to solve the final step of the problem, which is to make sure that I take the heat that I calculated and divide by the appropriate number of moles to get my final answer, which ends up being negative 332 kilojoules per mole. All right, so I'm going to zoom out real quick. First to say, does our answer make sense in this case? Yeah. The water was the surroundings for this problem and it heated up. So I kind of knew going into this problem that we should be getting a negative number for delta H because it should be an exothermic reaction if the surroundings are increasing in temperature. So that all seems pretty fine and dandy. But I want to scroll out a little bit more to show you that if you're able to think through these calorimetry problems systematically, every calorimetry problem is going to have a very different context, lots of different objects that are gaining heat or losing heat in the system. But common to all of them is going to be the same approach. If you can think through energy conservation and you can substitute in equations as appropriate and do the algebra, all calorimetry problems start to conceptually look pretty similar to one another. And so that's our summary for what we went over in today's video. My suggestion is that as you're solving calorimetry problems, don't first focus on what numbers to plug in where, but instead focus on how the underlying principles of heat conservation and temperature equilibration apply to your specific context, because that's going to give you an overall equation in terms of Q that helps you figure out where to plug in your numbers and how to solve for your given unknown variable. When you're doing those substitutions, we also saw that there's really only 3 choices for what to substitute for Q. So as long as you can pay attention to your units and whether we're dealing with a physical process or a chemical process, that'll help you know whether Q equals MC delta T, Q equals capital delta T, or Q equals delta H is most appropriate to help you solve for whatever your unknown is. That's it. Happy studying!